Hello and welcome to helpyourmath.com. In this video, we're going to look at graphing even more rational functions. And if you haven't already watched the previous video on graphing rational functions, you might want to, because while I do list the steps in the next slide, I'm not going to go into as much detail as I did previously. Here are my suggested steps for graphing rational functions. First, determine the domain. Then decide whether those discontinuities in the domain are vertical asymptotes or holes. Then determine any other asymptotes, whether there's a horizontal asymptote or a slant asymptote. Then find the intercepts of the graph. Then find a few points around each vertical asymptote to get a sense of the shape of the graph. And lastly, keep in mind that all of the pieces of the graph will be smooth curves. Let's look at some examples. First, we have the function g. G is defined by x squared minus 2x minus 8 over x squared minus 9. So first, let's figure out our domain. What do we know about our domain? Well, we know that the denominator can't be 0 because that's not going to provide us a real number. So we need to say that x squared minus 9 cannot equal 0. X squared minus 9, that's a difference of squares. That's going to be x minus 3 times x plus 3. Neither of those can equal 0. Set each factor equal to not 0 or not equal to 0. And we get x cannot be 3 here. And then this factor x plus 3 cannot equal 0 would be x equals negative 3. So we know there's two restrictions on our domain. X can't be negative 3, x can't be positive 3. The way we write that is we say the domain is from negative infinity to negative 3, from negative 3 to 3, and from 3 to infinity. Okay, so now we want to decide whether these are vertical asymptotes or holes. And the way we do that is we go back to our function and we want to factor the numerator. We've already factored the denominator. So the denominator is x minus 3 times x plus 3. And we want to see if there's any common factors between the numerator and denominator. So the numerator is going to factor into x minus 4 times x plus 2. And it doesn't look like we have any common factors, which indicates to us that the two discontinuities in the domain are vertical asymptotes. So we're going to say vertical asymptotes are x equals negative 3 and x equals positive 3. Okay, the next thing we want to do is to figure out what other type of asymptote there is. So this was kind of the first thing. Now we want to see if there's any horizontal or slant asymptote. And the way we do that is we look at first the degrees of the numerator and denominator. The degree of the numerator is 2. The degree of the denominator is 2. Since they have the same degree, that means we look at the coefficients of the leading, we look at the leading coefficients. So the leading coefficient of the numerator is 1, the leading coefficient of the denominator is 1, so there will be a horizontal asymptote, and that horizontal asymptote will be at 1 over 1, which we can just say is 1. Now I'm saying 1, but really I'm going to write an equation. So the horizontal asymptote is y equals 1. And what that indicates to us is that eventually, the graph is going to get really, really close to 1 on the y-axis, both to the left and to the right. But it is possible that the graph kind of leaps over it at some time. That's okay. The vertical asymptotes are like brick walls. Nothing's getting past those. But the horizontal asymptote, the graph actually can touch it and pass it. That is possible. Okay, the next thing we want to do to help us is find the intercepts. So we've done this. To find the x-intercepts, the way that we do that is we actually look at the numerator of the rational function and we set that equal to 0. Because if we have 0 over something, as long as that something's not 0, that equals 0. So what we're going to do is we're going to say x squared minus 2x minus 8 is equal to 0. That's going to help us find our intercepts. And we've already factored this. This is x minus 4 times x plus 2 is equal to 0. So this would be x equals 4. And this would be x equals negative 2. So we have two x-intercepts. We have one at 4, 0, and we have another one at negative 2, 0. What about the y-intercept? So to find the y-intercept, we would plug in 0 for all of the x values. And when we plug in 0 for all of the x values, the only values that are going to remain are those two constants. So I'm just going to go down here, since I'm already in my little x-intercept world or intercept world, and we're going to say that the y-intercept is given by 0, and then it's negative 8 over negative 9. Negative over negative is positive. So we're going to get positive 8 over 9 is our y-intercept. Okay, so we have our intercepts. I'm going to go ahead and graph all of this, and then we'll talk about figuring out what's going on around the asymptotes, because I think that'll be helpful to see Okay, so we have a vertical asymptote at x equals -3, and I'm going to do the best I can given that this is, upright. I can't really use a straight edge. If you have a straight edge, yours will turn out much nicer than mine. And we have another asymptote at y equals 1. And our x-intercepts, we have 4, 0, -2, 0, and then we have a y-intercept at 8, 9. So 8 9 is just shy of 1. Okay, great. So we have 3 kind of parts that these 2 vertical asymptotes leave us with. We've got this one over here, in between the 2 asymptotes, and then to the right of the furthest right asymptote. We don't have any points to guide us for this left. So we basically just need to plug in maybe 2 points, maybe 3 if you feel more comfortable. We just want to get some sense of what this graph will look like. So I'm going to plug in -4. And where do I have space for that? I'm going to erase my y-intercept. I'm just going to put the y-intercept down here just so it's there, but I would like that space. Okay, so I'm going to plug in -4 and -5. So if I plug in -4, I'm going to get, and I'll just do it there. So -4 squared is 16, minus 2 times -4 will be +8, because that's going to be negative times negative, and then minus 8. So those are going to cancel. I have 16 in the numerator. In the denominator, I have 16 minus 9, so I end up with 16 over 7. 16 over 7, that's 2 and 2/7. So -4, 2 and 2/7 will be maybe like right here. Okay, what if I plug in x equals -5? What does that give me? That's going to be 25 when I square -5. Then -2 times -5 is +10, minus 8 over 25 minus 9. So that's going to give me 35, 27 over 18. Yeah, that looks good. 27 over 18, that's 1 in something. So 1 in something will be like right here. So I have a sense, and we're going to use the asymptotes as guides as well. Probably this piece of the graph is going to stay above y equals 1. So I'm going to draw it, I'm going to have it close, and then it gets further, and then it's going to hug the x asymptote, and it's never going to cross that x asymptote. So that's what that left piece is going to look like. Now what about in between? So I have 2 points already in between, but in between the 2 asymptotes can do one of 2 things. It can kind of look like a parabola, where it can kind of go up and come back down, or it can kind of look like a cubic function where it starts down and then it goes up. And so we know that on, kind of to the left, it's going down, but we don't know what's happening towards the right. So we need to plug in either 1 or 2 for x to get a better sense of what this is going to look like. So I'll plug in 2. We'll get furthest away from it. And if I plug in x equals 2, that's going to give me 2 squared is 4, minus 2 times 2 is 4, minus 8. So those cancel, we get -8. And then in the denominator, I have 2 squared is 4, minus 9. So I end up with -8 over -5, which is +8 over +5, which is 1 3/5. So 1 3/5, where was I? 2 and 1 3/5. So this will kind of look like a cubic. It's not a cubic function. It's just going to kind of mimic one. And again, this won't be perfect, but I'm just going to do the best I can. It's coming down. It goes up. Notice how it crosses over the horizontal asymptote. That's okay. That's allowed to happen. Okay, and then in our third area to the right of the asymptotes, I see we already have 1 point. Let's just plug in 5. I'm pretty sure it's going to kind of, mirror the thing on the left, except be down, but we just want to make sure. We don't want to leave anything to chance. When I plug in 5, 5 squared is 25, minus 2 times 5 is 10, minus 8, over 5 squared is 25, minus 9. So that's going to be 15/7 over 25 minus 9 is, oh good lord, 16. So 7/16, so it's just shy of being a half. 5, so a half is going to be right there. So yeah, it's going to be a curve coming up from the asymptote. It's going to hit those 2 points, and it's going to probably hug y equals 1. So that's a rough sketch of what this graph will look like. Actually, it's pretty good. I have to admit I did a good job on that one. Okay, in our last example here, we want to graph the rational function. Oh, I didn't name it. Oh, let's call it h of x. There we go. H of x equals x minus 2 over x squared plus 2x minus 15. Okay, so we're going to do those same steps. Do you remember all of them? Of course you do. First, we're going to look at our domain. So what is the domain? Remember, the domain is going to have restrictions when that denominator is equal to 0, so it's x squared plus 2x minus 15 cannot be 0. We're going to factor this. This is going to be x plus 5 times x minus 3 cannot be 0. So now neither of these can equal 0. And so we get x can't be negative 5 and x can't be 3. So we have negative 5 and 3. So our domain is from negative infinity to negative 5, from negative 5 to 3, and from 3 to infinity. Okay, so there's our gorgeous domain. Now, what are these things? So we have x minus 2, that's already factored, over x plus 5 times x minus 3. It looks like they're both vertical asymptotes. So we're going to say vertical asymptote. And we're going to give the equations of the vertical asymptotes. Vertical asymptotes are always of the form x equals. So we say x equals negative 5 and x is equal to 3. So now we have those. Next, we want to see what else we have going on here. So we want to see if there's a horizontal asymptote or a slant asymptote. What do we look for? We start with the degree of the numerator, which is going to be 1, and the degree of the denominator is 2. When the degree of the numerator is smaller than the degree of the denominator, there's a horizontal asymptote at y equals 0. So we're going to have a horizontal asymptote at y is equal to 0. Okay, next we want to look for intercepts. So to find the x-intercept, remember what that means? That means I set the fraction equal to 0, and if a fraction is equal to 0, that means the numerator is 0, so we would say x minus 2 is equal to 0, and we end up with x equals 2. So we have an x-intercept at 2, 0. What about a y-intercept? So y-intercept, that's where we plug in 0 for all of the x's, leaving us with just those constants. When I do that, I get negative 2 over negative 15, which would be positive 2 over positive 15. So 0 and 2/15. Okay, so let's go ahead and graph all of this and see what's going on. I'm going to start with my vertical asymptotes, so I'm going to graph at negative 5. And again, the reason we do the dashed line is because these actually aren't part of the graph, they're just kind of helping us guide the graph. Right, it's a lot easier if we can just see something rather than have to try to visualize it. And y equals 0 is our horizontal asymptote. And what that horizontal asymptote means is that in the long run, towards all the way to the left and all the way to the right, the graph will just be hugging y equals 0. But in the middle, it could pass it. We don't know. Let's see. Okay, so what points do we have? We have 2, 0. Oh, look, it's touching right there. And we have 0, 2/15. So really, really low. Okay, we don't have a lot to go on. So we need a few points to the left of the asymptotes. We can look at negative 7 and negative 6. So if x equals negative 7, that's going to give me negative 7 minus 2 over negative 7 squared is 49 minus 14 minus 15. That would be negative 9 over, this is 29, so that's going to be over positive 20. So that's, like just about negative a half. So negative a half will be down here, a little bit higher than it. That was probably too high, but that's okay. And x equals negative 6, what's that going to give us? That's going to be negative 6 minus 2 over negative 6 squared is 36 minus 12 minus 15. That's negative 8 over 9. So that's closer to negative 1. That's really close to negative 1. Okay, do you have a sense of what this is going to look like? This is going to be a nice smooth curve that hugs the two asymptotes. So it'll kind of look like that. Okay, in the middle, yay for us, we have 2 points. I would calculate just one more point just so we see if it's going to be a parabola or if it's going to be kind of like that cubic-y shape. Let's plug in negative 4. Let's get really close to that vertical asymptote on the left. So if I plug in negative 4, I get negative 4 minus 2 over negative 4 squared is 16 minus 8 minus 15. That's negative 6 over, that's 8, negative 7. Negative 6 over negative 7 is positive 6 over positive 7. So we end up with a positive, so it's going to be that cubic-y shape. It's going to be pretty close to 1, but not quite there, except it's upside down, the cubic. It's not upside down, but this is just what it looks like. So it's like this, and then it kind of gets flat, and then it hugs that asymptote, right? These always hug the asymptotes. This side could be a little bit better, but if I erase it, the whole thing gets erased, and that wasn't actually terrible, so we'll leave that. Now on the right, we need to see what's going on. We're going to plug in 2 points to the right, so maybe I'll do 4 and 5. If I plug in 4, I get 4 minus 2 in the numerator is 2 over 16 plus 8 minus 15. This is 1, so that's going to be 2 over 9. That's pretty close to 0. So that's going to be like right here. Ooh, okay. And then what happens when I plug in 5? When I plug in 5, that's going to be 3 over 25 plus 10 minus 15. I think this is even smaller. This is going to be 3 over 35, 3 over 20. Okay, so this one, nice smooth curve, really close. Woo! Kind of something like that. Again, this is just the general idea of what it looks like. These have been a few more examples of graphing rational functions. Thank you for stopping by.